I open a new office hour slot for next week. From now on, or from now until I announce differently, given the number of rising cases of COVID-19 at university, among them a few colleagues and a few students, if you have heard it, I will have only online office hours. Just to stay on the safe side, it's pretty sure that at least people who are vaccinated will have, in 99% of the cases, mild forms of the illness. In particular, if we are younger than 60, still it will be a problem for everybody. If any of you is ill, and also, and it would be even worse if I get ill, because it's pretty difficult to have me replaced. Not because I'm the best professor at university, far from it, but the process of replacing a professor for 2 or more weeks during the course, it's pretty difficult to realize. That's the main reason. So for the rest, I hope everything is going to be fine. So today, we will start introducing matrices and connecting them with what I told you is a linear system, a collection of linear functions. And the objective of solving a linear system is finding all vectors, meaning all n-tuples, all coefficients, satisfying simultaneously all those equations. Among other applications, it's for what you will see in your career, at least among the compulsory course. Matrices are used in input-output analysis and pretty widely in statistics and in optimization as well. So today we are gonna have a fast review. We are gonna introduce matrices and defining somehow linear functions through matrices and connecting them with linear systems. Seeing matrices as functions, it's pretty useful because we have already developed some theory from functions, for instance, invertibility, which will be useful to tackle at least the solution of some linear systems. Something we will maybe be seeing in the afternoon. So remember, yesterday we introduced G vectors as simply elements of our N. We introduce operation between vectors, namely addition and multiplication by scalars, we introduce linear combinations that combine the two operations. A linear combination is a sum of two vectors obtained by multiplying by possibly different scalars two given vectors. We have defined linearly independent vectors. Linearly independent vectors are family or vectors providing non-redundant information, meaning that no vector of the family can be written as a linear combination of the other one. We have defined linear subspace at the end of the class. A linear subspace is basically a set of vectors that is closed under linear combinations, meaning all linear is a set V is a linear subspace of Rn if all linear combination of any pair of vectors of the set are still in the set. Among other things, a linear subspace is convex because if you see what was the definition, let me corollary a linear subspace is convex. So proof, you don't need to remember the proof. It's just to review what is a convex set. Proof. Let alpha between 0, 1 and a linear subset, say V, is convex. And let A be in two vectors in V. A linear combination, and so let's start from here again. Proof. So let E be in V. An element of the segment joining A and B can be written as alpha A plus 1 minus alpha B for alpha for some alpha in the interval 0, 1. So